Okay, central topic today. This is something that much of spin dynamics hangs on, both NMR and EPR, and this is something with which most calculations, more or less, are done in magnetic resonance, so density operator formalism. We've been through the wave function formalism in the previous lecture, and we saw that it sort of works. For one particle, two particles, you can drag it through. But as soon as you've got 10 to the 23 particles, the calculations would take the age of the universe to get through them. Maybe longer, actually, much longer probably. But anyway, so if you've got an ensemble of molecules, then it's the density operator formalism that you really need to use. So what I'll do today is I'll introduce the density matrix. To an extent, I will pull a rabbit out of the hat in the definition of it. It wouldn't come from anywhere in particular. If you dig deeply into the origins of it, it is related to the probability density of various states of the system. But really, in spin dynamics context, it does have very convenient explanation and interpretation, which we will get to after I've introduced it. So we start with the Schrödinger equation, as we normally do. So d psi by dt is minus I h psi. And I will switch to Dirac's notation here. So we'll just go d by dt psi will be minus I h psi. And in the previous lecture, I solved this in full generality for both time-dependent and time-independent case. So I will remind you that the solution at any specific point in time under the time-independent Hamiltonian is exp minus I h t psi of 0. And if the Hamiltonian was time-dependent, then we had an integral and a time-ordered exponential in there. So see the previous lecture for that. So this is our wave function, and this is the equation of motion for that wave function. And should we require the time-dependent expectation value of any particular observable, that, as we know, is an integral from minus infinity to infinity on any spatial coordinates there are of psi of x t Hermitian conjugate a operator psi of x t dx. X is just a coordinate or a collection of coordinates, which is short-handed in Dirac's notation like this psi a psi. So this is the Schrödinger formalism that we all know and love. And what we'll now do is introduce the density operator. So rho of t is defined thus far for no obvious reason as psi of t psi of t. Note the opposite direction of the Dirac brackets in here. It is actually a Kronecker product, so it's psi times psi transpose, and it is a matrix with these two vectors. Now it has a few properties. First of all, even though it is made out of two wave functions, it is itself actually an operator. That is, if we act with it on another wave function, so for example rho acting on phi, where phi is a wave function, as per the definition, will be psi phi. This is that sort of integral, so just a constant, it's a number. It will be a, then psi. So you see it acts on a function, should be, a psi, and it returns a function. And so it is an operator. Another property of rho comes from the normalization condition on the functions. You know that necessarily psi equals to 1, because 1 is the sum total of all probabilities in the system, or equivalent to the norm of that wave function. And so if we take rho squared, is rho. Rho is psi, 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 psi. This is equal to 1, and so we get back psi, psi, which is rho. So, without a square. So you see the rho squared is equal to rho. The operators with this property in mathematics are called idempotent. So raised to a power, they return themselves. And some operators you need to raise to higher power for them to return themselves. So if it's power k, then it's called idempotency index. It's the power of the operator, which when raised to that power makes the operator equal to itself. Right. Well, okay, so we've got our density operator, we introduced it, we looked at something basic. Let us now try and derive the equation of motion for it. So, what we are interested in, therefore, is its time derivative by dt rho. Well, as per the definition, that will be d by dt of psi. Psi. Product rule applies equally well to Kronecker products, so that will be d by dt psi, psi plus psi d by dt psi, and this we know. It comes from the Schrödinger's equation. Yeah? It's over here, or rather here. So d by dt psi is minus ia psi, and the complex conjugate of that situation is psi ih. And so when we plug that in, what we get is minus ih psi psi. So this part here. And when we do that, it will be plus psi, and that will be plus I think, and then psi h, the complex conjugate of the Schrödinger's equation. Okay, well, let's take a few things out of the bracket. Let's take this psi out of the bracket, and let's take this psi out of the bracket. And because various things don't commute here, we have to be careful to preserve the order. So that is minus ih psi psi plus I psi psi h, and we'll just return to our original rho notation because that is equal to rho. So that will be plus I rho h, that's this term, minus I h rho. And let's take minus I out of the bracket, minus I h rho minus rho h. Who remembers what this is called? Commutator minus I h commutator rho. So, start and the end, d by dt rho is minus I h rho. Most important equation in magnetic resonance. We will find Neumann equation. And the rest of the course we will be busy solving this beast in various guises and approximations and so on and so forth. Now, curiously, we already know the solution. You see, if we ask what is rho of t, turns out the answer is pretty simple. So, rho of t is, as per the definition, psi of t, psi of t. And what psi of t is, we actually worked out in the previous lecture. Here, it's the exponential. So, if we plug this into there, and this conjugate transpose into there, so what we'll get is x minus I HT, psi 0, psi 0, exp plus I HT. But this is the density matrix at time 0, and so exp minus I HT, rho 0, exp plus I HT. The famous double-sided exponential propagation. Yeah, you take your initial density matrix, you compute your exponential propagator with the Hamiltonian, you multiply it from either side by itself and its conjugate transpose, and we get the rho of time. Now, all parts of this you already know. We've spent 2 lectures exploring the various Hamiltonians. We've spent a lecture deriving the various constituent matrices in this Hamiltonian. So if you sit in front of MATLAB, you will be able to put together this matrix. The initial conditions we'll get to in a moment, but MATLAB would exponentiate you this into an exponential. And so the calculations, when done in this straightforward way, assuming your computer is big enough to cope with them, are actually very simple. You need to work out your Hamiltonian, you need to work out your density matrix. That's it. Yeah, the rest is a bunch of multiplications that the computer would easily do for you. Now, one other remaining thing that we need to find out is how do we extract information from here. That is, if we have an observable with an operator, we knew it was psi a psi to get the observable, but how do we do that for the density matrix? So, for that we'll need a bit of an index play. So that would be our observable. As we know in quantum mechanics, that is psi a psi, but we only have rho. Now, Dima can probably figure out the result anyway, because the trace of a scalar is equal to the scalar, and then you can switch the things around under the trace. But I will do it properly here. So if that's a vector, that's a matrix, and that's a vector, then this is defined, in fact, as a sum over ij psi complex conjugate I, a ij psi j. There's something here that I guess I should put an aside about. This relation is very useful. If you have A and B matrices and you want the ij's element of the answer, then that's a sum over k, a, I, k, b, k, j. Yeah? You contract the middle index in the product. Typically, these indexing situations only come out in the actual implementation of these codes, but this saves a surprising amount of time once you've sort of convinced yourself that that's the case. Right, so under the sum in each term, we can actually swap the terms around because they're just numbers. So what we can do is move psi over to the left. So ij psi I complex conjugate psi j, a I j. Now, but psi I psi j is a matrix element of this, and so what we get is the sum over I j, then rho I j a I j, and the only thing that we now need to do is to return it back into the operator notation using this. So for that we need the 2 indices not in the same order, but we need the middle index inside. And for that we just need to transpose things and conjugate them as well, because A is assumed. Well, I'm not actually assuming anything about it. No, I'm just saying that it's a conjugate transpose in there. So I j, rho I j, a j I, complex conjugate, and that is, you see, we take first the matrix product by summing in the first index, and then we sum the ith elements, so the diagonal elements of the product, and that's called a trace. So this is a trace of the product. So that is then trace of row A. Hermitian conjugate. And because you can permute things under the trace, what it's usually written as a Hermitian conjugate row. With hats in various places. Now, this Hermitian conjugate operation here is in a way moot because most observables are Hermitian. In fact, if you subscribe to a certain philosophical school, then all observables are Hermitian. However, it is required from a more general mathematical considerations. A scalar product on a space of operators must have a few properties, such as non-negativity. And it turns out that if you look at this as a general scalar product on a matrix space, then it is necessary to have this conjugate transposed just in case this observable might not turn out to be Hermitian. And it oftentimes does because when we do quadrature detection, we detect on X, this will be Lx, but then detect on Y, and then make complex linear combination of it. So we actually detect on Lx plus I Ly, which is L plus, which is not Hermitian. So it's a good idea to remember that this conjugation operation is in fact here, even though in many cases you can actually skip it. Curiously, and we did that when we considered the wave function formalism, we can actually expel the density matrix from the calculations entirely using this formalism. So if we look at the time derivative of the actual observable, using that equation over there, the observable operator itself is time independent. It's the density matrix that depends on time. So trace is a linear operation, so we just stick the derivative straight in. So it will be trace a Hermitian conjugate d by dt rho. D by dt rho is the little von Neumann equation. So that will be equal to trace of minus I h commutator rho. Opening that up, it's minus I trace a Hermitian conjugate h rho minus a Hermitian rho h. That, after we do the cyclic permutation under the trace, I guess I'll make another aside here. Trace A, B, C just happens to be equal to trace C, A, B. That's trace B, C, A. You can prove it as an exercise, but that's called cyclic permutation under the trace, that you can rotate products around. So taking I out of the bracket and a few other things, we'll get I trace of H a commutator, Hermitian conjugate times rho. And you see, this is an expectation value of this commutator, because that's the definition of the expectation values, trace of z times rho. So that is the expectation value of the H A. And so you see, d by dt A is the expectation of the commutator with the Hamiltonian, and so the entire formalism can be recast in terms of just observables and their commutators with the Hamiltonian, and this is why this is why we spent so much time with the commutators when I was introducing spin operators, because the whole formalism can be recast in terms of commutators alone. Okay, so let us then take a look at the physical meaning of this density matrix. It wasn't particularly clear so far. We only looked at the definition and mathematical properties that follow directly from the definition. Now let's try to interpret what it is that we've got in physical terms. As I mentioned in the previous lecture, because the density operator has got the wave function and the wave function conjugate transpose, the phase terms cancel. And so, unlike the wave function, the density operator actually survives the ensemble average. But for now, we will not actually ensemble average it. We will simply deal with that formalism as an exact, rigorous replacement for the Schrödinger equation type quantum mechanics, because you'll notice that I haven't actually made any assumptions or approximations in the entire derivation. So let's now take a look at the elements of rho. What is it that that matrix actually contains? So, first thing to do is to look at the diagonal elements of rho in a particular basis. So let's say we have chosen our basis of some wave functions, which may or may not be eigenfunctions of the Hamiltonian, but they just correspond to some states of the system. So let n be a particular state of a spin system, yeah, a particular basis vector. Then let's take a look at n element of rho. So rho n is, as per the definition, n rho n. Expanding rho in its original definition, that is n psi n, where n is the state that we are interested in and psi is the state that the system is in. So that is the coefficient of psi n inside psi. That's the coefficient and its complex conjugate. So that is the absolute square of the corresponding expansion coefficient, and the absolute square in quantum mechanics of the coefficient is the probability, yeah, Pn. So it turns out that in a particular basis, the diagonal element of rho gives the probability of the system actually being in that specific state. Which is quite useful, and in a continuous representation that would be probability density, and this is where the name density matrix is coming from. The off-diagonal elements are a bit less clear. Textbooks actually are very fuzzy on the subject, or perhaps they just over-interpret what's going on in there. So let's say we have a wave function which is composite, yeah, a linear combination. So the system lives in a superposition state, Schrödinger or something. So it will be some linear combination, and it will have two terms that we'll specifically take a look at. So the nth term and the kth term. Yeah, the cat can be dead, the cat can be alive, the cat can be dead and unhappy, alive and happy, and so on. But yeah, amongst the linear combination, there are these two terms. So when we then look at the density matrix, rho, that will be psi, put it in, multiply together, it will have a big bunch of terms. And then 4 terms that come out of the multiplication, it will be Cn absolute square n n. Something that we already discussed, so diagonal element, then Cn Ck conjugate k plus Ck Cn conjugate k n, and it's a probability term for k, Ck absolute squared k. So if the system was in a pure state, this would have been non-zero, and the rest would be 0, yeah, if it were only in the state n. If it were only in the state k, then this would have been non-zero, and the rest would have been 0. Those are probabilities. However, these terms only appear if the system is in a mixed state. So if both Cn and Ck are non-zero, then these terms would be non-zero. And this is a term that lives on the nth row and kth column of the density matrix, so it's an off-diagonal term. So the strict and defuzzified conclusion that we have is the off-diagonal terms in the density matrix simply indicate the presence of a linear combination in the original wave function. So that we are not entirely in one state, but there's a linear combination in the wave function. For ensemble it would mean something different, but for our purposes now, the diagonal elements of the density matrix have probability of being in a particular quantum state, and the off-diagonal elements indicate the fact that the wave function is a linear combination of the wave functions corresponding to those states. Right. So one other, perhaps, aside here is the sum of all probabilities must of course be equal to 1 for a single quantum system, and the sum of all diagonal elements is a trace, and so what we conclude is that trace of rho must actually be equal to 1. Always. However, curiously, if you look at quantum mechanical density matrices of spin systems, you don't find that. All Pauli matrices are traceless. The reason for that is this trace doesn't actually evolve in any way, in any kind of dynamics, because it commutes with the Hamiltonian. So what is customary to do is to take the density matrix and replace it with the density matrix minus the unit matrix. I think that's just it. Times k, with the k scaled in such a way as to have the trace of k times the unit matrix equal to 1. So essentially we subtract a little bit of unit matrix out of the density matrix to make it traces. Unit matrix commutes with everything, and so in the Liouville-van Neumann equation, d by dt minus I h rho, if unit matrix commutes with the Hamiltonian, it doesn't contribute to the time derivative and therefore does not contribute to system dynamics in any way. It just sits there. All observables in quantum mechanics Pauli matrices are traceless. And when you multiply a unit matrix by a traceless matrix and takes a trace, it's 0. So the unit matrix contributes neither to system dynamics nor to system observables, and is therefore physically completely inconsequential. And so it is therefore customary, sometimes as a matter of, I guess, historical convention, other times as a matter of making the system numerically a little bit better behaved, to have this trace out. There are also algebraic reasons in that the SU and algebra is spanned by traceless matrices. And we'll get to those algebraic reasons in the next term, but for now, I guess just take my word for it that because the trace is in that way inconsequential, we just usually kick it out of the system. Right, okay, equations 14 and equation 15 put a little bit of rigor to the statements I've just made. Well, I guess let's just do that. Let's prove the fact that the trace is physically inconsequential. So d by dt acting on rho of t plus any amount of the unit matrix, because this is a constant, differentiates to 0, so that's the same as d by dt rho t. So the presence is inconsequential on the left-hand side of the Liouville-van Neumann equation. And for the right-hand side, similarly, I guess I wouldn't actually draw it. The unit matrix commutes with everything. And so it actually is 0. And for the observables, so if we have an operator A, that is a trace of A Hermitian conjugate rho. If we add or subtract a little bit of the unit matrix, trace of A plus A times rho plus K times the unit matrix is equal to, because trace is linear, trace A emission conjugate rho plus K trace A times the unit matrix. As I said, all observables in spin dynamics are traceless, so that's just trace of A conjugate, that is 0. So that's back our trace A rho. So it doesn't affect any dynamics or any observables, and therefore can be disposed of. Right, moving on. Another thing that I guess all of you remember at least hearing is our laboratory jargon. When we say that a particular system, let's say in the LZ state. Yeah, but LZ is an operator. It's not a wave function. So how can we actually say that? So the next little snippet will illustrate something that doesn't really have a name. I just invented a name for it, called operator state duality. And it is possible to demonstrate that if the system is in a state with a particular value of a particular observable, then its density matrix is just equal to the corresponding operator with some condition. Which makes it incredibly useful because if the system is polarized on Z and not polarized on X and Y, we simply instantly conclude what its density matrix is because it's equal to LZ. And now we'll get a formal proof to that statement. So, say we've got our density matrix, yeah, psi, and let us say our psi, yeah, our wave function is spin up alpha. That is 1, 0. And that is clearly a situation in which the system is magnetized along the z-axis. Let us now take a look at what the corresponding density matrix will be. So, psi, that is 1, 0. Psi conjugate transpose, 1, 0. This is a Kronecker product. You can see it's the terms are wrong way around for a vector-vector product. So Kronecker product is just take this matrix, multiplied by each element of that matrix and stack them together. So what we've got is 1, 0, 0, 0. This is not traceless. So remember that we need to kill the trace. And to kill the trace, we need to subtract a little bit of unit matrix out of here. And if we subtract 1/2, 1/2, the result will be traceless. And so we kill the trace. 1/2 minus 1/2, 0, 0. That, in fact, is LZ, the Pauli matrix for the Z magnetization. So you see, we've started with the system on Z. This is one of those situations when we know that it's on Z. We looked at the density matrix and it's equal to LZ. If we had started with the system on X, it would be, I think, 1, 1 and 1 over root 2 in here. Did the same mathematics, we'd get Lx. So the bottom line here is if a system is in a state where a set of observables have got a set of their own values, then the density matrix is a linear combination of those operators with those coefficients. And so if we say, okay, the system's in LZ, rho equals LZ, that makes it very, very easy to generate the initial conditions for all those equations. Yeah? Because typically we start with a magnetized system that's relaxed, and it's all on Z, and every nucleus is on Z, and so the initial density matrix is typically just the sum of all Z and every nucleus. If we apply the pulse, it will all be on X, so we can do that. So you see, one of the advantages of this density operator formalism is this neat relationship between what the density matrix is and what the observables of the system are. Whereas it was rather difficult to extract the vector for the wave function because you really have to do a lot of guesswork to find out what the wave function is for a particular combination of observables. And so in this way, and this will be the topic of the next lecture, next Friday's lecture, product operator formalism, where we will be exploring this convenient fact rather a lot. Okay, the second thing that you have all heard about is something that we call superoperators. And the original reason for them is, if I remind you the solution to the Liouville von Neumann equation, x minus IH t rho 0 x plus IHT. I guess I will not explain why exactly, but in numerical calculations, the fact that this product is double-sided is very inconvenient. If you have multiple such products nested, they will be nested on either side. Every element of this row depends on every element of this original thing in an obscure way. So when you're doing numerical calculations, it is in many cases extremely inconvenient to have it this way. In particular, things like group theoretical operations on these propagators become big and hairy. Various sums in here don't open very well. And so one particular simplification that people often make is to try and find such a replacement for the Hamiltonian as would have a single-sided propagation operation. So let's say this is our H. So the question is, can we find such an H, and it has a double hat for the reasons I will get to in a moment, as would have the following. Rho of t is x minus I h double hat t rho 0. So we would replace a double-sided multiplication with a single-sided multiplication. It turns out, after a very considerable amount of algebra, that such a form does in fact exist. And it is called a commutation superoperator. Now, a superoperator is something that acts on operators. So if we have our H rho, yeah, that's a commutation by H, we can generalize it a little bit. Why don't we look at a class of such commutation operations? So H, comma, empty place. Clearly we can put any operator in here, and the result will be the commutator of that operator with the Hamiltonian. So this is a transformation, and if you apply it to a set of density matrices, it transforms that set somehow. So it is an operator that acts on other operators. For that reason, it's called a superoperator, and is in fact called H double hat. And so if we want H rho, it's actually H double hat rho. Now, the explicit form of this I will derive, but I will derive it in the second term. In the course on the mathematical foundations of spin dynamics, it's to do with a lot of Lie algebras and a lot of complicated indexing transformations. But so the transformation recipe between our standard operator notation and this superoperator notation is the following. Take rho, matrix, and stretch it into a single vector column-wise. And stretch into a vector in the following way. If this is our row, and these are our columns, column 1, 2, 3, 4, and so on, it is stretched like that. So it becomes a vector. And the second step is H double hat is equal equal to H cross E minus E cross H transpose. Very non-trivial thing to derive. But E is the unit matrix of the same dimension as the Hamiltonian. And so what that gets us to is we get from our Liouville von Neumann equation, so d rho by dt is minus I h rho, where this was a commutator and the solution was in terms of a double-sided multiplication. It becomes d rho, and because rho becomes a vector, it's customary to use Dirac's notation for it. By dt is minus I h superoperator rho. And its solution is in terms of a single-sided exponential. And so, can somebody tell me what this looks like? Schrödinger's equation. So we went to density operator formalism. We can now describe ensembles. We can now have those convenient properties in terms of observables. And then we stretched it back into a form that effectively looks like Schrödinger's equation. And the same method that have been used to solve Schrödinger's equation can be used to solve this. So this representation in the jargon is called Liouville space. And this in the jargon is called Hilbert space. Not to be confused with the mathematical structure called Hilbert space, which is a metric space. So when we say Hilbert space formalism in spin dynamics, that's this, with its double-sided exponentiation. When we say Liouville space formalism, that's this. The great advantage of this is in the numerics. This single-sided multiplication really makes life an awful lot easier in practice. The other great advantage is this formalism supports various relaxation and decoherence models. It is not possible in general to have this with accurate relaxation model like Redfield theory. Redfield theory, and again you may have heard the phrase relaxation superoperator, intrinsically belongs to this formalism because it's an even more general superoperator than the commutation superoperator. So Redfield 1 is in fact a linear combination of commutation superoperators, so it's a more general thing. So it belongs here.
No.
Yes.
But if we are in the Liouville space, the dimension of the space is the square of the dimension of
Much bigger. Yes.
And the exponential is
Much
still
more expensive.
Okay, so but it's still
True.
worth to do.
Correct. There's no denial, yes, that under Kronecker product, the matrix dimension squares. So Liouville space formalism is much bigger, but interestingly, as of late, last 5 years or so, we actually found that quite a few of these elements are either never populated or never changed. And in the original density matrix, if you find an element that isn't getting populated, it doesn't reduce your dimension at all. You just poke a hole in it, but it stays the same dimension. However, in here, if some element is not populated, you can actually destroy it and reduce the dimension. And so in practical calculations, we found that Liouville spaces often get reduced to the kind of dimension that's actually smaller than the dimension of the original density matrix. So, but in the most general case, you are of course correct. Calculations in Liouville space are much more expensive. But with relaxation theory, we don't have a choice. Really. It's a series that is intrinsically formulated in Liouville space. So we just bite the bullet by a big computer. Go for it.
Can you please explain again what is the numerical benefits of the computations in Liouville space compared to the computations solution of the same Schrödinger equation in a smaller space?
I can give you an example. Many properties that we need, in particular in spin chemistry, are integrals from 0 to infinity of a certain observable. So observable in question is the so-called singlet yield. So the amount of a chemical system that is there in a singlet state. And because it reacts, we need to take the total amount of the reacted species, which is an integral. So what we will have is an integral from 0 to infinity of a trace of our singlet projection operator with the density matrix. So rho of t dt. If we have a double-sided exponentiation in here and a trace, then this will be equal to the following. The integral from 0 to infinity, trace we can take out really, it will be s e minus I h t rho 0 e plus I h t dt. Do you think of an analytical solution to this? Doesn't exist, or rather it only exists in Liouville space. So through the same transformation. So okay, let us now reformulate the same problem in Liouville space. So what we will have is integral from 0 to infinity, singlet state vector, rho t dt. That would be singlet out of the integral because it's constant. Integral from 0 to infinity, e minus I h double hat t rho 0 dt. Rho 0 out of the integral forward because it's a constant. S integral 0 to infinity exp minus I h double hat t dt rho 0. The integral of an exponential is 1 over the Hamiltonian times the same exponential. Usually we have a bit of a relaxation superoperator here, so I'll just add a little bit of r just to make sure it's regular, but let's just say it's already there, so to avoid singularities on the inverse. So that's 1 over minus I h s rho 0. Yeah, on the infinity we assume it has decayed to 0, on the 0 it's equal to 1, and so the answer is s I s h minus 1 rho 0, and h minus 1 times the vector can be computed much more efficiently than just h minus 1 and then times the vector. And so, whereas the corresponding trick, you see that my trick was that I took the density matrix out of the integral because it could be pushed out forward. In this case I can't do it because this is exponential in the way. So certain things are analytically, if not numerically, a bit easier in Liouville space.
You explained perfectly why the computation with a superoperator in Liouville space is better than the computation with the density operator and two-side multiplications.
Mm-hmm.
But we started from the Schrödinger equation for the wave function,
Mm-hmm.
and now we have the Schrödinger equation for the density operator.
Correct.
So what is the difference here?
Ensemble averages. Wave function goes to 0 under ensemble average. Density vector doesn't.
And
We can now deal with 10 to the 23 system.
right.
Okay. So, final topic for today is composite systems. So, we have been through all the necessary matrices for an individual spin. Yeah, we know them. They're Pauli matrices 2 by 2, easy to type into a computer. What happens when you've got 2 spins, 3 spins, 4 spins, and so on? There are 2 answers. One you have seen already, the addition of spin with Clebsch-Gordon coefficients. Don't use it. It's only there for historical reasons, because people didn't have big computers those days and had to do things analytically. Big boys like ourselves with big supercomputers do things with Kronecker products. And still in the individual spin representation, because really going into the total spin representation is in our case unnecessary. So, how do we do that? As you remember from quantum mechanics, if we take 2 independent systems with wave functions psi A and psi B, the total wave function is a product. Sometimes symmetrized, sometimes anti-symmetrized, but it's a product. So that will be psi AB. For the density matrix, we can just work it out explicitly, but before we do, I'll give you a couple of relations between straight and Kronecker products. To remind you what they are, a simple matrix product is you take two matrices, you multiply this row by this column, like that, sum it together, and that's your element here. For the next element, so if it's n case element, you multiply nth row here and case column here, sum together, and that's your element. That's the standard matrix product, yeah, denoted by a dot. Kronecker product, denoted by a cross, is you take this matrix, this entire matrix, multiply it by this element, and stick it into here. So the result is a much bigger matrix. With this matrix multiplied by each element of this one and slotted together. So you can see why Liouville space is expensive here, because the matrix dimension goes up an awful lot. So that's the difference between the straight and direct product. And let's now write a few relations between them. You can prove it. I will not do it on the board. This is a magnetic resonance course after all, not an algebra. That A cross B times C cross D is in fact equal to AC cross BD. Understandable a bit more once you deal, I guess, in your life enough with vector spaces, but for now that's just it. And another important property is the trace of A cross B is trace A, trace B. You can see how this can save a lot of computing time. Yeah, by computing individual traces rather than the trace of a direct product. But well, let's just remember these properties and do a little bit of math with the density. My time is running out, but the handout is as well. So rho of AB will be, as the definition suggests, psi AB, psi BA. That we work out in terms of the products. So that will be psi A cross psi B, and then psi A cross psi B. And once you've worked it through and reintroduced the density matrices in the end, you'll find that this is rho A cross rho B. So wave functions multiply, but the density operators get a direct product. Hamiltonians, however, behave in a very interesting way. HAB is HA cross E plus E cross H B A B. You see, this comes from the fact that the Hamiltonian of A must still only act on A, has no business acting on B. So this thing, when it acts on that, because of this property, HA will act on A, and a unit operator will act on B, so nothing will happen to B. The B part of the Hamiltonian will act with a unit matrix on A, nothing will happen, and will act with the HB on B. So such a form of the Hamiltonian ensures that the part of the Hamiltonian that worked on A continues working on A, and the part that has worked on B continues working on B. No derivation here, it's a bit involved, but there goes. So wave functions multiply, density operators cross it, Hamiltonians undergo this. And this gives you a complete set of instrumentation. You know what the Pauli matrices are, so you know everything about a single spin. You know what the Hamiltonians are, you can put those Hamiltonians for every single spin, and then you know how to put them together to make a multi-spin system. Once you've made the Hamiltonian and the density operator for the multi-spin system, you use this entire formalism to solve the solution forward, take the trace with your observable, and that's your free induction. So we've actually covered the basic fundamental formalism of spin dynamics, and from this point onwards, it will be specifics and applications. Okay, any questions?